For the second example, we're going to assume that we have 100 molecules of air, and we note that the standard conditions for part A are at 1 atmosphere and 273 Kelvin. So if we assume 100 molecules, then the average molecular mass for air, we can write that as capital M, is going to be the 78% times mass of nitrogen plus the 21% mass of oxygen plus 1% mass of the argon. Percent means for every 100, so we can rewrite this as a decimal in the following way. And assuming that air has a molecular mass of 29 grams per mole, then using the ideal gas law, we can find what the number of moles is. So that will give us PV over RT. And since we have standard conditions, then the pressure is atmospheric pressure, which is 1.01 times 10 to the 5th Pascal. The volume could be per cubic meter. We can adjust that later if we need to. The gas constant R is 8.314 joules per mole Kelvin, and the temperature is 273.15 kelvins. And if we carry out this calculation, we find out that we have about 44.5 moles of air. And now, what we can say is that the mass of our sample is the number of moles times the molecular mass of our sample, which is 44.5 moles times 29 grams per mole, or the same as 1,290 grams or 1.29 kilograms, which means that the density is the mass over the volume. And if we use 1.29 kilograms divided by the assumed 1 cubic meter, then we get 1.29 kilograms per cubic meter. Notice that we used 1 meters cubed because we were going to find the density, and it's already per unit volume, so we could have assumed the volume to be 1. For part B, we're asked to find the density of air in a hot air balloon that at a different temperature. So we're still going to assume that the pressure P is 1 atmosphere. We're still going to assume that the volume is 1 meters cubed. And now the only thing that's going to change is the temperature from our equation. equation. So we have PV over RT, but now the temperature is the temperature of the hot air balloon. So if we plug in these numbers, we get 1.01 10 to the 5th pascals times the 1 meters cubed divided by the gas constant times the temperature, which is 120 plus the 273.15 kelvins. And now if we do that, we get about 0.896 kilograms, which means since the volume is 1 meter, that the density is 0.896 kilograms per meters cubed.